All right, so electrochemistry, the last chapter that we're going to talk about in this book. Is it hard? Well, I'm not the best person to ask, right? No, it's not hard, but there's some vocabulary that you have to get under your belt, okay? Balancing these types of reactions we're going to talk about is not difficult. The practical applications for what you can do with these things, understanding how to build a battery, is not difficult. Predicting these reactions is a little nasty. I'm not going to lie to you. I'm not going to sugarcoat it. But lucky for you, the chances are that they ask you about one of these reactions on that exam pretty slim. Right? Those aren't the ones that they're going after. Electrochemistry, I'm going to try to do it as much justice as I can, but this is not really my favorite subject. It's a little dry. I mean, to sit here, discussing batteries is not my favorite thing. Biochemistry is more my thing, but I promise you, I will do my best to explain this to the best of my capacity. All right, so first things first, you have to understand that electrochemistry is all about redox reactions, and redox is a mixture of two words. It's oxidation and reduction. So in redox reactions, one of the things that has to happen is that electrons have to be transferred from one species in the equation to another. And then one of the things that you need to understand is that redox reactions that are spontaneous are capable of transferring energy. And usually the energy is in the form of electrons. And if you can harness that energy by getting those electrons to travel down a wire, you create electricity that we can use to drive all sorts of lovely electronic devices and machinery and equipment that we've gotten so accustomed to using in our modern everyday lives. Redox reactions can also transfer energy in the form of heat, but really we use them in their electricity creating capacity. So really we're going to spend quite a bit of time talking about A, how batteries are made, how they function, B, how we can electroplate things based on some of these principles that we're going to learn. You guys know what electroplating is, right? Was that a yes or a no? All right, so if you buy a person a Christmas gift of a gold necklace and it says electroplated, is that quality jewelry, or should you send it back? Oh, it's cheap. What electroplating is they take just a really cheap metal to make the core of the necklace, and then they use electricity to deposit a very thin layer of gold on top of it. So it's not gold all the way through. So eventually that electroplated piece of jewelry, the gold will wear off on your skin just from rubbing, and what's left is the cheap stuff underneath, all right, which will turn your skin green if you've got a nickel allergy. So never accept a piece of electroplated jewelry as a gift. Always send it back. All right. So anyways, non-spontaneous reactions, like electroplating, can be forced to happen by giving them electricity. So the spontaneous ones give up electricity. The non-spontaneous ones, you can make them happen by giving them electricity. And we're going to do like 3 Pogels this week that you'll understand why that is. And they're all going to be in the context of Le Chatelier's principle, right? So they're just applications of that principle. All right, next. So not all redox reactions, not all reactions are redox reactions. So reactions in which there has been no change in oxidation number are not redox reactions. And I know it's a little bit hard for you to see up on the board, but here's some examples. I put down 2 examples and then 2 non-examples. Let's take a look at the examples first. So in this first example, I've got elemental sodium coming together with chlorine gas in the synthesis of sodium chloride, right? If I were to calculate the charge for sodium, that has a charge of 0. Let me see if the light helps at all. Can you see that a little bit better now? Elemental sodium is going to have a charge of 0, right? Because all elemental things have a charge of 0. But over here, in the form of sodium chloride, what happened to the charge of the sodium? It became +1. And the same with elemental chlorine. On the left-hand side, it had the charge of 0, but then on the right-hand side, it became an ion, so it became -1. When an element or an atom changes charge like that, that's redox. All right? Okay, take a look at this next one. What kind of a reaction is this? Rubidium plus lithium chloride yields lithium plus rubidium chloride. That's a single replacement, right? So this first one was synthesis. This one was single replacement. All right, do we get a change in charge again? Yeah, we sure do. Rubidium on the left-hand side is in the elemental form. On the right-hand side, it became the ion. Whereas lithium on the left-hand side was an ionic form. On the right-hand side, it became elemental. Rubidium had to give up an electron. Lithium was the recipient of that electron. All right? Take a look at these non-examples down here. Oh, what kind of reactions do you see here? Not that you can see it, but... Well, they're both double replacements. The bottom one is a special kind of double replacement that we just spent 2 chapters talking about, right? Neutralization. If you were to calculate the charges for each individual atom, both on the left side of the arrow and the right side of the atom, you'll notice that none of them change charge in the process of switching around. These are not redox reactions, right? So by and large, you already know how to predict many redox reactions because we spent quite a bit of time at the beginning of the year figuring out how to write products for synthesis and single replacements. All right? By the way, combustion reactions are also redox reactions. You know how to predict those already. We still have a small subset of redox reactions to learn how to predict, and that can be a little bit on the sketchier side. Okay? All right, so long as you just write this first sentence and then you write down that things that are redox are things like synthesis, single replacement, and combustion, we're good. And then double replacement are not redox. That's all you need to do. You don't have to write all these equations down. Again, this PowerPoint will be on Blackboard for you. Okay? All right. We need to learn some terminology. So, and we're also going to start writing equations with electrons included. So oxidation is the process in which element becomes more positive. It attains a more positive oxidation state. And you should know that oxidation state is just fancy for charge. It's fancy language. Okay. All right, so if sodium is becoming more positive, what has it done? In order to become more positive, what did it have to do? Lose an electron. Where do you place the electron if you're losing it? On the right-hand side. Why? Because you want that charge plus that charge to equal 0. Okay? All right. Well, where does that electron go? It goes to chlorine. As chlorine undergoes reduction. These reactions are coupled. For this one to happen, this one must happen, and vice versa. All right? So reduction is a process in which an element attains a more negative oxidation state. All right? Actually, this reaction has to happen twice to satisfy one of those. Right? So this process has to occur 2 times for this process to happen. All right, so what happens in chlorine? Elemental chlorine absorbs an electron that's given up by sodium. Actually, it has to absorb 2. Right? And then it turns into chlorine minus. So that process, to go from 0 to -1, it had to gain electrons. Actually gain 2 electrons. Well, you have to demonstrate that by adding 2 electrons on the left-hand side, because again, you want the charges on the left to equal the charges on the right-hand side. All right? I have a really difficult time keeping these definitions straight in my head, because I'm kind of silly that way. So I have a stupid mnemonic device that I always remember. That says Leo says Gur. All right. I think you have another one in AP Bio that you know something about oil and something about oil slicks. I don't remember. No. Okay. Leo says Gur. Basically, what that stands for is that you lose electrons in oxidation, you gain electrons in reduction. And as a matter of fact, I use this all the time. Yesterday, I was working on some of the Pogels that I'm going to have you do this week, just to kind of preview them. And one of them asked me to draw like a picture of a battery, and I still had to think in the back of my head, Leo says girl, Leo says, to figure out what goes in the cathode and what goes in the anode. silly, but I have to do it. All right. All right? Let's move on. You got it down? All right, so redox reactions are really the culmination of two half reactions. So this is the overall equation that occurs when you take sodium, elemental sodium, and chlorine gas, and you synthesize sodium chloride out of it. When it comes to balancing an equation like that, though, we have to take these overall equations and split them into two half reactions. All right? So usually what you do when you go to balance these things, you'd have to split up this overall process into the half of the process that demonstrates the electron being lost, and then the other half of the process that demonstrates that lost electron being taken in again by the other partner. All right? Okay, so when you start with splitting these things in half, what you really have to do is start by assigning charges to all of the atoms, both on the left of the arrow and on the right of the arrow. And then you focus on, for instance, the oxidation first. All right? So according to Leo, right? Leo says grr. What does oxidation mean? You lose electrons, right? So which of these two elements is losing the electrons, the sodium or the chlorine? The sodium. All right. So what I'm going to do is I'm just going to write the parts of the equation that only have sodium in them. All right? So I write sodium plus Na1 plus, and then in order to balance out the charge, I have to include an electron on the right-hand side. Okay? All right. And then I focus on the reduction half reaction. So Leo says grr, 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 gain electrons in reduction. So which of these two things is gaining the electrons? The chlorine. And so then I just write what is in the second half of the reaction, just the substances on both sides of the arrow that include chlorine. So you write chlorine with a charge of 0 on the left, chlorine with a charge of -1 on the right, and then in order to balance out the charge, you put an electron over here on the left. Okay? So this is how you split up the reactions into two halves. Let's spend a little bit of time learning how to predict these reactions. All right. So some of this you already know because we've gone through this. So you already know how to predict the products of synthesis reactions. You've already learned how to predict the products of single replacement reactions. You already learned how to predict the products of combustion reactions. Here's something that's really pretty obvious. What are the kinds of elements that undergo redox? Well, active metals, right? So when I say active metal, what families am I talking about? What am I talking about? Alkali and alkaline earth. Well, why are they good candidates for redox? Because they lose electrons easily. All right? And redox, the whole process of redox is all about giving up electrons, taking in electrons. All right? Okay, what about active nonmetals? What family am I really talking about specifically? Halogens. These are good candidates for redox reactions. Well, why? Because they gain electrons easily. You can't have this happen without having that happen in the same beaker. They're coupled. These reactions are always coupled. You have to have one partner giving something up, the other, another substance in that beaker, taking that something in. And that something, that currency, is electrons. Okay? All right? Okay. Perfect timing. I'm recording this. It'll be on Blackboard. But why don't you guys pull out that Flynn reactions packet that we were working on, because that's part of your homework. I'm going to help you with 3 questions, and we'll talk about how to answer them. There are 2 slides on this PowerPoint that I'm going to make available to you. There's this one and then the following one. There's some tables here. You're just going to need to have these out handy when predicting products of reactions. Okay? So there's 3 questions that I actually want to go over with you from this reactions packet. And so tonight you're going to have to do questions, what was it, I to K? I to K are complex ion things. All right, and then we're going to, for homework, you have to do NO, and then U to Y. And pretty much we'll be done with all the categories of reactions. All right. But I want to go over at least 3 of them with you, just to show you how to use these tables to predict these products of redox reactions. And again, some of this is really, some of it you know, some of it you're going to have to rely on your photographic memories. So the first one that I kind of want to go over right now is W. And it's hard to see up here, so I'm going to rewrite it on paper so that everybody can read it. Okay. All right, so the reaction says that I have, this is W from that Flynn packet, right? It says, oops. Hydrogen gas, so I'm going to write H2, is passed over hot iron 2 oxide powder. All right, so that should be pretty straightforward. You should recognize exactly what it is that you're supposed to do there, right? What did you learn that was? What does that look like? Single replacement, right? Okay, so in a single replacement reaction, what do? The hydrogen switches with iron. All right, so iron over here was +2. Now when it switches, it's going to become elemental. How do I write elemental iron? Fe, all right. And then now over here, the hydrogen was elemental, but now over here it's going to become ionic. What is the charge for ionic hydrogen? We just spent 2 chapters talking about it. 1+, right? And so that ionic hydrogen coming together with the oxygen that's also in ionic form, which is, it has a charge of 2-. So H1+ with oxygen 2-, what do we make? H2O. Easy peasy, right? When you see something that looks like a straight up single replacement reaction, when you see something that looks like a straight up synthesis reaction, when you see something that looks like a straight up combustion reaction, do it the way you learned before. All right? That's not going to change. You can go ahead and balance those things. It'll be fine. All right? There really are some special ways that we balance these things, but I don't think that those particular types of reactions will be affected too much. All right, well, where things get a little bit sketchier are things like N, all right, on this Flynn packet, the homework that you have to do tonight. And what it says in N is that you have a solution of potassium iodide. So first of all, what does that indicate to you? A solution of? That these ions floating around. And I'm electrolyzing it. All right, so what does electrolyze mean? I'm zapping it with electricity. So if I have to give it energy, guess what kind of a reaction this is? This is a non-spontaneous redox. All right? Well, what do I do with these things? Beats me, I don't know. Let's take a look at this table. There's something here about halogens. Free halogens, so when they say free halogen, they mean in elemental form. They turn into halide ions. Okay. And then let's take a look here. So what is this? Is this a free halogen? No, what is it? Halide ions. And we said we had to give it electricity to go in reverse, right? So what do you think a halide ion is going to turn into? Free halogen. Okay, so how do you write iodine in elemental form? I2. So free halogen means element. All right, so that's one thing that happens. What had to happen to the number of electrons here for it to go from I minus to I with the charge of 0? What happened here? Did it gain or lose electrons? Guys, it went from negative to a more positive thing. Did it gain or lose electrons? It lost an electron. All right, so someone had to gain it. Who gained it? The K. All right, so if potassium gains an electron, what happens to its charge? It becomes neutral, right? So it becomes the elemental form of potassium. And if you look at the table, look, metal ions, if we're going in the non-spontaneous direction, what do they turn into? If we're going in the non-spontaneous direction, because we have to give them electricity, that means we're going from right to left. What do metal ions turn into? Free metals. All right. So you're going to use these tables, essentially, to figure out what's formed in the reaction. So these are some important oxidizers. If you find these as reactants, these are things that you form in the reaction. So if you weren't electrolyzing them, you'd be going left to right. Because we are electrolyzing them, we're implying that we have to add energy to the system to get the reaction going. So we're doing the reverse reaction. In that case, we're going to go from right to left. We're going to start with these things, turn into that. You just figure out the products from the table. All right? Are you supposed to memorize this? No, you're supposed to have a photographic memory. Here's my suggestion to you. Know that basically halogens and metals, they're going to switch back and forth between their ionic form and elemental form. Okay? And then the other thing that you should be familiar with, I would be familiar with permanganate. Take a look. All these important oxidizers with transition metals, what do they have with them? They have oxygen associated with them. When they turn into something, what do you notice? They lose the oxygen. So really, what I would memorize this one, that one, and then the nitric acids. And then you're going to go into the exam and pray that they don't give you any of these questions. A lesson on how to save stuff on your calculator. The problem is that you're not allowed your calculator on this section of the exam. Sorry, they're called flashcards. For this Flynn reaction packet, I would just look at this while I'm doing it and hope for the best. And again, the key to these questions is to get as many points as you can. If you don't get all the points, we're fine. Just get as many as you can. All right? Get at least half of the points. We'll be good. All right, let's take a look at one more. Let's take a look at X. It says an acidified solution of potassium permanganate. All right, so potassium permanganate, it's a solution of, so I can split it apart. And let me just make a little note on the margin here is that it's an acid. And I'm going to mix it with sodium nitrite. It's a solution of sodium nitrite. All right. Okay. All right. Well, how do I use this table to figure out the products? Oh, did they give me like permanganate and acid? Yeah. Well, what does that turn into? Mn2 plus. All right, that's my product. So the manganese changed charge. Okay. And then what about? By the way, we can figure out how much that charge changed. Let's see, what is this? -8. Oh, this was from +7. I'll show you how to calculate that in a sec. All right. So I went from the manganese here went from +7 to +2. So what did it do in that process? Lost electrons. So somebody here has to gain electrons, and a lot of electrons at that. Okay, what about NO2? Let's take a look here. Is NO2 on this list? nitrite, right? Anyone see nitrite on this list? Oh, ooh, look, second table, nitrite ions. What do they turn into? Nitrate ions. All right, well, that's the other product. And let's see. This is gaining electrons. If I calculate this, I bet this is, I'm going to show this losing electrons. So if you have one species gaining electrons and the other species losing electrons, then probably these things are spectator, the potassium and the sodium. So I'm just going to write them on the right-hand side and cross them out. Because you really only need one to show one thing gaining, one thing losing. All right? At this particular point, you might notice that, okay, well, there's 8 oxygens on the left-hand side, but only 3, 8 on the left, but only 3 on the right. How do you account for that? You can't go ahead and change the coefficient in front because then that's going to throw off your number of nitrogens. We're going to do some funky balancing by adding waters to this, but I have to explain to you how to balance redoxes. But at a minimum, using this table to figure out what some of these products are is a start. Okay? So I want you to try these questions on that Flynn reactions packet using these tables, and these tables will be available to you. All right? So this entire PowerPoint will be available. All right? As the recording of what we're going over right now. Yes, ma'am? Well, I'm going to show you how to balance today, so you're going to do your best to include those. All right? Okay, so let's spend some time. Yeah, so this is really, again, this is one of the reasons why this is my least favorite thing to talk about, is because a lot of this depends on just brute memory, memorization of stuff and rules. I'm not a fan of that. All right, so let's talk about how to balance. And before we balance, the first thing that we have to do is do a quick review of how to assign oxidation numbers. So oxidation numbers is fancy code word for charge, right? Charge. To balance these things, you first have to assign charges to every atom in that equation. All right? So some of these rules you know already. You don't have to write this all down. All right, so first things first. If you have something in elemental form, what's its charge? 0. All right. The oxidation number of a monatomic ion equals its charge. All right, so you know that, right? So what's the charge of sodium ion? +1. How do you know that? You memorize that. What's the charge of the chlorine ion? -1. How do you know that? You memorized it. The charge is the oxidation number. The oxidation number of oxygen in compounds is 2-. The oxidation number of hydrogen in compounds is 1+. All right, and I really hate this PowerPoint because the signs were, I stole this PowerPoint from somebody, and they put the signs up front. You're supposed to put the signs on the back end. All right. This is stuff you know. Nothing new. Oh. Well, what if you're not sure about what the charge is for something? And these are not the best examples. What if you had, for instance, say, sulfur trioxide? What if I want to know the charge of sulfur here? How would I figure it out? Well, what's the charge on sulfur? Well, you'd say it's 2-, but there's a problem, right? What's that problem? What's the charge on oxygen? 2-. Can you have 2 negative species come together and stick magnetically? No. And you also know that sulfur does funny things, right? Remember when we were doing Lewis dot structures? Can sulfur take more than 8 electrons in its valence shell? Yeah. Why? Because it's got those d orbitals that are available to it, right? And so sulfur could have a positive charge. How could you calculate its charge? I'm not 100% sure that I know the charge of sulfur. The further I go to the middle of the periodic table, the less sure I am about the charges of elements. Well, I'm not too sure about sulfur, but I know the charge of oxygen, because I just told you in the previous slide that it was, what? 2-. All right. Well, can I do some math to figure out what this charge actually is? It's not negative. I know for a fact it's not, because 2 negatives are going to repel. All right, well, I do some math. It requires a little algebra. So what I do is I take the number of sulfur atoms, and I multiply that by x, because I don't know its charge. and then I add it to the number of oxygen atoms in that formula, and I multiply it by the charge of oxygen, which happens to be 2 minus, and then I take all that and I set it equal to 0. Well, why 0? It's a compound, it's electrically neutral. All right? Well, how many sulfur atoms are there in this formula? So 1x plus, how many oxygen atoms do I have in this formula? 3 times negative 2 is equal to 0. What must x be? It's plus 6. That makes a lot more sense. A positive thing will magnetically stick to 3 negative things. In this case, it's not really an ionic bond. It's covalent, but I mean, you get the gist, right? So you're going to have to do this business of calculating oxidation numbers for things that you're not certain of because they weren't in the previous slide by doing this kind of math. And you have to do it for every atom in a compound. All right? There's a couple of other examples here for you. Here's how you figure out like the charge of calcium, oxygen, and hydrogen. It all has to add up to 0. All right? Now, what if you had to figure out the charge, for instance, of nitrogen in nitrate or the sulfur in sulfate? You do the same thing. It's the same math. All right? You take the number of nitrogens, and again, the nitrogen I'm kind of weary about. Why am I worried about nitrogen? Because it's closer to the middle of the periodic table than oxygen. Oxygen is closer to the extremes. Things that are on the extremes, I'm pretty confident that I know the charge about. The further you go to the middle, things get kind of iffy. Because you don't know if it's going to if it's going to be more convenient for it to lose electrons or gain electrons. Because you're getting to that, you know, that valence shell that is almost half full or half empty, right? So you're going to have to do some math. So again, here in this particular case, I've got 1 nitrogen whose charge you don't know. It's coming together with 3 oxygens whose charge is minus 2 because I'm confident in that. The difference is here, I didn't set it equal to 0 anymore, right? Why not? Because these are polyatomic ions. You set them equal to the charge of the polyatomic ion. All right? And so then if I solve for x, then that oxidation number, or that charge for that nitrogen, is plus 5. So in this particular ion, nitrogen chose to become plus 5 in lieu of becoming negative 3. It was more convenient to go this way in this particular compound, or ion. Yes, Omar?
It's just like add 8 to the next charge, like negative 3.
Yeah, it's not going to be that straightforward because we do have some ions in there that have 4, 5, 6 different charges. It's not always going to be just 2 choices, 1 or 2 choices. All right, here's sulfur. Sulfur and sulfate, what's its charge? Same thing. You have 1 atom of sulfur, whose charge you don't know, plus 4 oxygens with a charge of minus 2. They add up to negative 2 because that's the charge on the polyatomic ion. If you solve for x, x is plus 6. So in this particular case, sulfur is plus 6. So I think in one of the last Appendix F set of questions that you had to do, this was one of the things that they asked, and some people were kind of clueless about what they were being asked to do. That's all that you had to do is calculate charges. All right. Okay, let's talk real quick about how to balance redox reactions. Here's a redox reaction. All right. So this first thing that you do is you assign oxidation numbers to each atom in the reactants and products. And again, don't write this down. This is on the PowerPoint. You'll have it available to you. All right. This was already done for you. So this is a reaction where we have iron and tin reacting. Iron is going from plus 3 to plus 2. Tin's going from plus 2 to plus 4. And the first thing that you do is you rewrite them as half reactions. So you write the oxidation first, and then you write the reduction. So again, the oxidation is the one where you're losing electrons. The reduction is the one where you're gaining electrons. All right? You're just basically taking this equation and splitting it into 2 lines. All right? Okay, so step 3, what you do is you balance the atoms. All right, so if there had been 2 Fe3 pluses over here, then you would have put a coefficient over there on the right-hand side. You have to make the number of atoms equal because we still have to follow Lavoisier's basic law of conservation of matter. But in addition to balancing atoms, now we also have to include electrons in this process. All right, so to go from plus 3 to plus 2, what must you do? Gain an electron. All right. To go from plus 2 to plus 4, what must you do? Lose 2 electrons. So you put them on the right-hand side. The key here to balancing redox reactions is that at the end of the day, not only do you have to balance atoms, but now we have to balance electrons too. All right? Okay, so are these number of electrons the same? No. We have to make them equal. All right, so how do you make that equal to that? Multiply by 2. So you're going to take that first line and multiply it by 2, so that now you have the same number of electrons on both half reactions, which then allows you to add the two equations together, and in the process of adding the two equations together, you would end up with 2 electrons on the left and 2 electrons on the right, which you treat them like spectators and cancel out. That's balanced. Okay? So there's an extra step in here in balancing electrons. All right? It gets a little bit trickier than this, though. Because then they're going to start doing some stuff like this, too. They're going to ask you to balance it in acid. And then they're going to ask you to balance this in base. Some of these reactions don't occur unless the pH is low or the pH is high. All right. So they'll say to you something like this. So you've got permanganate and chlorine under acidic conditions turn into chlorine gas and manganese 2+. All right, well, how do I balance this mess? All right, I've reassigned the order of what I'm going to do. So like steps 1 and 2 are like the reciprocal of what I showed you on the previous slide. All right. So what I usually do first is really I assign oxidation numbers first. So let's take a look. Well, what's the oxidation number here in chlorine? -1. What is it over here? 0. Over here it's 2+. All right, well, I need to assign oxidation numbers here for the manganese and the oxygen. Well, what do I know the charge to be for oxygen? 2-. All right, so now I need to figure out what the charge is for manganese there. All right, well, I've got 1 manganese with a charge of X plus 4 oxygens with a charge of 2-, all totaling a charge of -1. So what does X have to be for that sentence to be true? 7. So it's going from 7+ to 2+. All right. Okay, so first things first, I'm going to write the 2 half reactions. So usually I wrote the reduction first, right? So this is the reduction reaction, half reaction. This is the oxidation half reaction. But it doesn't matter what order you do it in. All right, so you see how manganese is changing from +7 to +2? So write every compound on the left and on the right-hand side of the arrow that contains manganese. That's one half reaction. All right? And then in the other half reaction, chlorine is going from -1 to 0. You want to write every compound on both the left and the right side of the arrow that has chlorine in it in the second half reaction. Okay? All right. Now, step 2 says assign oxidation numbers and use this to rewrite half reactions, including electrons. Well, I already came up with the oxidation numbers. So let me just rewrite it down here. Okay, so we went from +7. Oh, wait a minute. After you write the half reactions, you have to balance the atoms, right? So my original equation didn't have a coefficient of 2 in front of the chlorine minus, but I had to put 1 so that you had the same number of atoms on both sides. Sorry, that's an important step. Don't forget that one. All right, so next, let's take a look at this first equation. So to go, I have 1 atom of manganese on the left, 1 atom of manganese on the right, correct? To go from +7 to +5, I'm sorry, to +2, what must I have done? Gain 5 electrons. So I'm going to add 5 electrons on the left. Okay? All right. Now, in terms of chlorine, ignore that 2 in front and that 2 on the bottom for just a moment. To go from -1 to 0, what must you have done? Lost an electron? That's 1 atom losing an electron, but how many atoms do you have doing it? 2. So how many total electrons did you lose? 2 electrons. So you write 2 electrons on the right-hand side. All right? Okay, so once you have the electrons written here, you've got the number of atoms balanced. Now we got to figure out what to do to both of these lines to get the same number of electrons in both of them. All right? So what is, how do I get the same number of electrons in both of these lines? What's the common multiple between 5 and 2? 10. So why don't we try to multiply that top line by something that will give us 10 electrons and multiply that bottom line by something that will also give us 10 electrons. All right? So essentially that's what I do is I take that entire top equation and I multiply it by 2. So I put a 2 in front of the permanganate, a 2 in front of the 5 electrons, and a 2 in front of the manganese. And then I'm going to take that bottom line and I'm going to multiply it by 5. So 5 times 2 chlorines plus 5 yields 5 chlorine gases plus 5 times 2 electrons. And once I multiply through, I add the two lines together. And what I'm left with is 2MnO4 plus 10Cl minus yields 2Mn2 plus 5Cl2. All right? Okay, great. You might notice at this stage that there are some oxygens present on the left that are obviously missing from the right. So we're breaking Lavoisier's law. All right? So how do we fix that? Simple, simple. How many oxygens are present here that are on the left that are missing on the right? 8. Simple. Isn't this happening in the presence of water? Yep. So I'm just going to add 8 waters on the right-hand side. Fabulous. My oxygens are accounted for. All right. However, in the process of adding these waters, I've just introduced yet another atom on the right-hand side that's missing on the left-hand side. Right? There's some hydrogens here that are absent over there. Well, how do I fix that? Well, lucky for me, this is an acid. What's floating around an acid? Hydrogen. So you would add 16 hydrogens to account for those. All right? This is a real pain in the tush. But it's really not that bad. Again, this PowerPoint will be available to you with all the steps. Just follow the steps. Okay. All right. Well, what if they ask you to balance this sucker at a base? So step 1. So like for instance, they tell you nitrate and aluminum in basic conditions makes ammonia and aluminum hydroxide. This is a complex ion reaction. Well, you would balance it as if it were an acid. So you assign oxidation numbers to everything. You write your 2 half reactions. You balance out your atoms. You balance out your electrons. You add the 2 lines together. All right, and then you're left with this mess. Okay, so in this particular case, you had to add 23 waters to get your oxygens to equal out, and you had to add 5 hydrogens to get your hydrogen ions to get your hydrogens to balance out from the waters that you introduced. All right, but here's the problem though. What's the pH of something that has an accumulation of hydrogen? It's low. What do they tell you? It's in base. You can't leave that there. Okay, well, that has a really simple solution. If I have 5 hydrogens floating around on the right-hand side, then what I'm going to do is I'm going to add 5 hydroxides to both sides to get rid of them. Right? What do these 5 hydroxides do to these 5 hydrogen ions? Turn them to water. Right? So now you've got water on the right-hand side, hydroxides on the left-hand side. Now this is consistent with being in a basic solution. All right? The issue, though, now is that now I've got water on both sides. I've got 23 waters on the left side, 5 waters on the right-hand side, and technically you have to reduce those water molecules, so then you would subtract 5 waters from both the right, and you subtract 5 waters from the left, all right? And then you're left with this final equation. All right? So you treat it as if it were an acid. You add hydroxides to eat up the hydrogen ions, and then you reduce your waters because you have water on both sides, and you're not allowed to do that. You want to get rid of the spectator ones. Okay. All right, that's it. Fun, right? Okay, so again, homework tonight is do those Flynn reaction questions. Do the 2 questions on page, what is that, 8? I can't read that. 838. And then there was a POGL on work that I did not get back from the printer. You need to print that out from Blackboard and do it. It's actually very simple. One of the things that I should warn you about that particular POGL is it's a beta version. It just came out. There are some questions that will say to you, go and do these calculations and fill in the table, and you're going to go to the table and find that it's already filled in. Consider yourselves lucky. My suggestion is, for those questions where the table's already filled in, why don't you look at the answers that are on the table and just make sure that you understand why they are what they are. Okay? Just confirm that you get the same answer if you were to actually do the work. Okay? We'll pick up from that point tomorrow.